If you're going to give me more, it's fine.
Yes, I'll give you the 5 minutes. Okay, I think we can restart. So we'll hopefully be in time. So we start the Blazar session now, and so the first talk about Blazar science in the LSST era. So we'll have first the invited talk, and then we'll have a series of contributed talk. Please.
Oh no, I have a microphone.
Yeah.
Yeah. So okay. Hi everyone. So I was asked to talk about Blazar science in the LSST era. And as you might imagine, the possibilities here are really endless. So in the interest of time, I thought I'll just give you a couple of the sort of standard bread and butter science cases we're going to be pursuing. And I'll mention a little bit about some more exotic science that LSST will enable us to do. So, but before I do that, let me tell you a little bit how different from the ATN we've been here. So you might know that have a jet is pointed directly to the light. That is really what makes them special and what makes them very bright and very variable across the electromagnetic spectrum. That also means that we really only see the jet. We rarely get anything from the accretion disk, and we rarely even see the host galaxy. So what you see up there, oh, sorry, wrong button. That is what a typical spectral energy distribution for blazars looks like, which has these two broad emission components. The first one is from relativistic electrons that have been accelerated in the magnetic field of the jet and make synchrotron. We think this is coming from a region that's away from the black hole. We call it the blazar zone. And again, we think that this is a recollimation shock in the jet flow, but there could be other interpretations as well. The second component, which goes from X-rays all the way to TV gamma rays, that is something we don't fully understand and is connected to the matter content of the jet and how jets are formed. So if, for example, you have a Blattner-Snide jet, you can have a lot of electrons, and electrons make high energy radiation through inverse Compton scattering. Now that can happen in many different locations around the jet, and we give it a different name, but it's essentially the same process. If you have a Blanford-Payne jet, then you're going to have protons. And protons make synchrotron, or they interact with other protons. Other photons make secondary particles, and it's then the secondary particles that produce the X-rays and gamma rays that we see. We don't really know exactly where this will be happening, but if you take the simplest case that you have a proton synchrotron emission, that will most likely come from the blazar zone where electron synchrotron comes from as well. That is also related to the multi-messenger emission we might be seeing from blazars. And of course, if that's gravitational waves, they're going to come from a binary. But blazars are also candidates for high energy neutrinos and ultra high energy cosmic rays. And the association between the two is very uncertain. And even more uncertain is where and how those high energy particles will be produced. And I'll tell you a little bit towards the end how LSST can actually help us address this problem. So that's true for all AGN, but it's especially true for blazars that we cannot be looking at a single wavelength. We have to look at the broader multi-wavelength, multi-messenger picture. And we are very lucky that in the coming 2 or 3 years, we're going to have a lot of very exciting experiments in the southern hemisphere that will really cover that range. So from radio all the way to TV gamma rays, and LSST is really sort of in the center of it, bringing everything together. And of course, the name of the game here is variability, like in all AGN. And blazars have a lot of different types of variability that we can see. Now, we've heard a lot of talks about finding periodic variability. That is also sort of a hot topic lately for blazars as well. But whereas in the normal AGN that comes from a binary, for blazars it can come from many other different mechanisms. So for example, you can have a jet that's precessing, or it is wobbling, and that will also give you sinusoidal variations. You can have kink instabilities that are forming at the jet boundary, and as they propagate down the jet, they cross shocks and they give you quasi-periodic oscillations. Or again, as in all AGN, you'll just have red noise processes that will give you things that look wavy, but there's nothing really there. So it's not only important for us to find this signals, but it's also important to understand where they're coming from. And so far, our best sort of candidate for that has been OJ287, which shows this 11-year outburst in its light curve. But lately, we've been finding more and more, let's say, compelling cases for periodic variability. And what is really interesting is that they show very different behavior. So here are two examples where the top one is source code PKS 2131 that has very clear variability in radio, but we've seen recently that it also shows the same variability patterns in other wavelengths. So I'm showing you here the ZTF light curve, but we also have evidence that it follows the same pattern in infrared and gamma rays as well. We have some evidence, other evidence for that, but we think this is in fact a binary system. If, on the other hand, you look at this corner, that's BG5053, and that shows periodicity in gamma rays. And you can see here the gamma ray light curve and the sort of the 2.2 roughly year outbursts that we see. Now, when we look at the other multi-wavelength light curves, we don't find evidence for that periodicity or similar patterns. So in the first case, whatever is happening is really affecting the whole jet. In the second case, it only affects the gamma ray emission region. And as we were discussing with Antonio in the first day, we don't really have any good explanation what would be causing that just yet. So we hope that LSST will not only help us find more of the sources I've said, but also help us understand the signature we see in other wavelengths as well. Now, I think the most sort of standard analysis we're going to be doing is cross correlations. And that not only tells us about the emission regions in the jet and how they're oriented or distributed across the jet, but it also tells us about the underlying high energy emission process. So here's an example of an optical and gamma ray light curve from a source, which looks a little bit noisy. But if you actually do the cross correlation analysis, that's the discrete correlation function, you see that there is a very clear peak at a time lag about 0, which means that basically optical and gamma rays vary in tandem. If you then do this exercise for a few tens of sources, you will see that there is, in fact, a very strong trend in the population for time lags about 0, which is what you see here. So this is also telling us that we're most likely looking at inverse Compton scattering and electrons. But that is when you look at the full light curve. When you actually start going deeper and looking, on a flare to flare basis, situation get a lot more complicated because we have what we call orphan gamma ray flares. And here are a few examples where you see the gamma ray flares in red, and there is not really any response in the optical, which you see with the blue and the black lines there. Those are kind of hard to explain with at least a simple inverse Compton scattering model, and they are not really that rare. We estimate about 1 in 5 of gamma ray flares is in fact orphan. So there are quite a few. Now, our biggest issue is that we don't really have enough sources that we can do this exercise reliably and starting actually building up large statistical samples. But there are, at this moment, about 3,000 gamma ray blazars in the southern hemisphere that just wait for the optical data to come along. I've been telling you how we play with other wavelengths, but there's a lot we can do with just the optical data we're going to get from LSST alone. And this is how a blazar looks like in optical. And these are different bands. They're not exactly the same as the LSST, but they pretty much cover the same wavelength range. So as you can see, there are major outbursts every 1 to 3 years, where the source becomes about 20 to 30 times brighter, and then it goes back to quiescence within a few days to a few weeks. Now, what's interesting is if you take to adjacent flares, those don't really look the same. And one of the reasons for that is, or at least what we think might be happening, is that we're looking at different mechanisms that produce the flaring episodes. So if you have nicely sampled multiband optical data, you might actually be able to differentiate between things and figure out what is going on. So if you take these two flares, for example, one of the easiest games we can play is just try to split up the flare into a sort of quiescent level and flaring part and see how its spectrum in the optical changes over the flare. And that tells you a lot about particle acceleration and cooling processes that take place, and might be able to point to the mechanism for the acceleration as well. You can also look at color variations across the flare. And what you see here is just optical band versus optical band. And if you see these straight lines, that means that you have a new emission component showing up, causing the flare. That could be a shock, could be something that could, propagating inside the jet. Whereas when you see this sort of curved lines, that means that most likely you're looking at Doppler factor variations. So the beaming changes and causes flares. That could happen if the jet moves around, or you can have some bends or kinks in your jet and material just flows through it, causing the flare. So just with the optical data, we can probe structural changes and fine structure in the jets. Very interesting. Now, one of the science cases that LSST will really enable is the study of the host galaxies. And I've told you just a few minutes ago that we don't really care about the host galaxy, and that is because we don't normally see it. Now, if you have a big enough telescope of a long enough baseline that the source will, become dim enough, you might be able to start seeing something. Now that is important because not only it will allow us to study the host galaxies, the environments, and maybe at some point figure out why all blazars are in elliptical galaxies, but it will allow us to do much more. And there is a significant fraction of the blazar population, which we call BLAC type objects, where we don't see any spectral lines. So there's no way for us to know their distance to the source. And if you can get images of the host, you might be able to at least place some constraints on that. That is very important because I just, it so happens that these BLAC objects make very high energy gamma rays. And as those gamma rays propagate through the universe, they see the extragalactic background light and they get attenuated. So there's a maximum energy in the gamma rays you can get from a given source, given its distance, which is what you see here. So that's sort of the maximum gamma ray energy versus redshift. And that envelope is really that extragalactic background light. And it's very sensitive to the properties of that, which are in turn very sensitive to the matter content of the universe and the expansion rate. So if you have good constraints on your EBL, you can actually turn them into constraints on the cosmological parameters. And this is a recent attempt trying to do that. Now, you might have heard that cosmologists don't really agree on the value of the Hubble constant. So having completely independent constraints could be very, very helpful to figure things out. And this is really going to be enabled from the fact that LSST will give us the host galaxy, but at the same time, we're going to have CTA in the southern hemisphere, giving us the very high energy gamma rays. So I've told you about periodic and a random variability, but there are many other forms of variability we can see in blazars. And here is sort of one example. This is a source called PKS 1413, and this is the radial light curve, which spans almost 45 years. And what we see is this sort of U-shaped dips happening in the light curves every so often. They happen across different frequencies, and they also seem to be symmetric. So here's a zoom in of one. You can ignore the lines for just a minute, where the black points that you see are the normal data, and the open symbols are the mirror data. So it's the same exact data, but with the time going backwards. And as you can see, they seem to fall right on top of each other. Blazars don't really do that. That is not, they don't make symmetric looking things. Uh, so this is a very standard blazar by any account, except one tiny little thing. It is the only blazar we know of that seems to be in a spiral galaxy. If you remember from a minute ago, every other blazar is in an elliptical, which is a little bit strange. Now, we have other evidence for that, but we think that what we're looking at is actually microlensing. So we have the blazar, which is somewhere back there. We're down here. And what we see as the host is, in fact, just an intervening spiral galaxy. So every time you shoot something from the jet and it moves downstream, it makes light. The light crosses the caustics of the lens, and we get this nice U shape. And in fact, just a year ago, we were able to model all the different dips across different frequencies with the same fixed lens model. So we are a little bit more confident that this is in fact microlensing. Now, if that's true, then it will be very interesting because it will give us the ability to probe milli-arc second scales in the jet, and it will also help us probe lens masses, which are in the 10 to the second to 10 to the fifth solar mass, which can be a very interesting mass range. Now, we've not been able to confirm that behavior in any other wavelength because it's too faint, but by too faint in the optical is about 20 magnitude, which is not going to really be a problem for LSST, of course. And this object was found by accident in a sample of about 1,000 sources. So you can imagine if you have a few thousand to play with, you're bound to find more such cases. So it could be very interesting. Now, finally, let me tell you about neutrinos, as I promised in the beginning. And this is work we've been doing with Puya, who's a graduate student at the Finnish Center for Astronomy with ESO. And we're trying to cross-correlate blazars with the arrival of neutrinos on the sky, but also we try to look at what happens in those blazars when the neutrino arrives. And I have two examples here, where at the top you see the radial light curve, and the middle is the optical. This magenta, the solid magenta line is the arrival time of the neutrino. So as you can see in the first case, the neutrino comes in a bright radial and optical flare, whereas in the second case, we only see it coming at a radial flare. There's no really, not really anything happening in the optical. So that is, if these associations are real, it's telling us that most likely the neutrinos are produced away from the black hole on parsec scales. But none of this, I'll be done shortly. None of these associations are true, really, or sorry, we don't know if they're true. They're not significant. These are at the level of 2 to 2.5 sigma, but there are many reasons for that, and one of them, or two of them, let's say, is we don't really have enough sources that we can do this reliably, and we don't really have enough neutrinos. We're only getting alerts at the moment from one telescope, which is IceCube in the South Pole. Now, just a couple of years ago, they started building two new telescopes in the northern hemisphere. This is KM3Net and BICO. They're still being built, but they're already getting data, and BICO has already issued a couple of alerts. But you can imagine just in a couple more years, they'll be in full swing, and they will need telescopes now in the southern hemisphere to follow up on the neutrinos that they find. And of course, LSST is going to be the best for the job. So just to summarize, I told you a bit about the bread and butter science cases, but I don't want to be misunderstood. This is not really going to be business as usual. LSD will really push the limits of what we can do with blazar science, both in terms of the quality and the quantity of the data. But what I think is a lot more important is that it will really enable new and very exciting science cases. And what I've told you is basically what I could come up with and things that we have hints from previous surveys. I'm absolutely certain that when we actually start getting the data, there is a lot of more things that we'll discover and a lot of new interesting behavior that we can follow up. Thank you very much.
Questions?
May I ask this question? How do people do the rapid follow-up if that interesting event's happening from the other facility? Especially radio is important for the Blazar science. But if it's really fast turnaround times, do you have successfully follow up with the radio for those events? Kind of.
So that's a good question and a lot to think about. But what the way we've been operating so far as the community is that you have pretty much fixed monitoring programs that monitor a large number of objects, and then we just communicate with each other. You have ATELs, you have things that you tell people to sort of follow up. That is obviously focused on the northern hemisphere, and not all blazars are making all this super bright outbursts. So we have a list of sources that you kind of expect to be doing the crazy things. But the truth is that we not really have a lot going on in the southern, and this is things that we need to think about and take care of before LSST starts.
Yanni, you showed a plot where you can constrain the Hubble constant with the blazar flares.
Well, constraining at the moment is not.
Well,
it's not
but how?
just the gamma rays at the moment is the green curve in case you missed that.
No, but how does it work in practice? So presumably you get the host, you get a spectroscopic redshift. And
You
then
cannot get a spectroscopic redshift. That's the point. You get an estimate for the distance of the source, and then you can sort of sorry, let me go back. Then you can sort of place it here. That's why you see some of those have fairly big uncertainties. But that's why you need a lot in order to statistically then be able to constrain things in some way.
So thank you very much. I never realized that blazar are expected to be in ellipticals. But if now we have blazar at redshift 6, how do we have ellipticals at that redshift? I am not able to imagine it.
I can tell you that from the sources that we can see the host galaxy to some people, they're all elliptical. I don't think we're able to see host galaxies at redshift 6. So I don't know what's. They could be, but all the nearby sources that we can actually resolve, or all the BLAC objects that we can actually see, they're all. We have no idea why.
Would I be correct in my suspicion that what you're calling elliptical, you actually mean early type galaxy? That is the absence of a spiral. Therefore, it could be a lenticular galaxy, and lenticular galaxies can be built from mergers of spiral galaxies. So you could have a dust-rich merger-built system where the gas has all fallen to the center and turned on this system.
Sure, but we don't know. That's the thing. Like, we don't really see much of the host galaxy to be able to tell things apart. We just see the light profile, and it matches best an elliptical profile.
If the top right's a light profile, I would say that's PSF and an underlying galaxy, right? I wouldn't be calling that elliptical. I think it matches better if it's lenticular, and I don't think it disagrees with anything you've said.
I wouldn't know. I'm not an expert in the host galaxies. I think that this is going to be a very interesting science case for LSST to pursue, and finally maybe figure out what's going on. But like I said, the current consensus is that these are all ellipticals.
Before we move on, I have a question as well. Maybe it's naive, but how do you distinguish if you have, for instance, a processing jet from a binary system?
That's a very good question. You cannot really, unless you have sort of other evidence. For example, you can see VLBI and resolve the jet, and we see them moving around. So, for example, in this source that I showed here, BG5053, we see that the jet is moving around quite a bit. For PKS, we don't. So you're trying to sort of maybe exclude scenarios at this point, but in reality, unless you have some other information, just by the light curve, you cannot really say if it's binary or not.
Okay, we have to move on. Let's thank Ioannis again. Next talk is from Claudia.
Yeah, I have this things here. No. Okay.
Yeah, with the title
I don't have
so
this
long
one.
that I know you did it on purpose to confuse me.
You got it.
It's 30 years of Blazar studies from the Torino Observatory, in short.
Sorry. So, I would like to briefly tell you the story of Blazar studies at the Torino Observatory, which now covers 30 years. And I introduce the main characters. Besides me, I must mention Gabriele Ghisellini, who was here in Torino at the very beginning, that Maribel Carnerero, who came here 12 years ago, and finally Massimo Villata, who has always been here and active. And the story began in 1994 when CCD was mounted on the main telescope of the Torino Observatory, and we decided to start to monitor a sample of gamma loud blazars. And the reason was that in 1991, the Compton Gamma Ray Observatory was launched, and it discovered that the extragalactic skies is full of blazars. Blazar can be powerful gamma ray emitters. Soon we joined the OJ94 project, which was led by the Finnish team. And the aim of this project was to monitor OJ287 in order to be able to confirm or reject the quasi 12-year periodicity of the main double peak Alberts that were predicted by Silam et al. Back in 1988. And the next two peaks of the hours were awaited for fall 1994 and winter 1995. And we could actually observe them. You see the light curve here that we published in Silam et al. 1996. And besides observing, we also propose a model to interpret this periodicity, and according to which we propose that there's a binary system of supermassive black holes, and both of them are launching a jet, which is and processing, and each time one of the two jets points towards us, we see a flare. And this comes from the fact that the flux that we observe depends on the emitted flux by some power of the Doppler factor. And the Doppler factor depends on the viewing angle. So that when the jet viewing angle decreases, the Doppler beaming becomes stronger, and we see a flare in the light curves. The breakthrough went in 2000 when Massimo became the president of the Whole Earth Blazar Telescope, and I became the WEBT executive officer. The Whole Earth Blazar Telescope was founded by John Matos in 1997, and his idea was to have a network of optical observers that could provide the optical monitoring of the targets which were observed by the Compton Gamma Ray Observatory. Under our leadership, we expanded the WEBT also to include radio and near-infrared observers, And we organized several massive multi-wavelength campaigns, often in conjunction with satellite observation. And we also have active collaborations with other teams, Agile, Fermi, Magic. The web has grown, and we have now members in many countries around the world. The main threat of the web uh, is its capability to get really well sampled light curves because of the distribution in longitude of its member. And this was clear since the beginning. Here you can see the folded light curve of BLAC in 2000 during the first massive web campaign on BLAC, which was led by Massimo. And you can see here that we can follow even the details of the variability of the object. 20 years after, in 2020, another web campaign led by Svetlana Jorstad, again on BLAC, which is our favorite source. You can see that the light curve is very well sampled, and we were able to identify periodic oscillations during the first phase of the outburst, and the period was about 30 hours, and these quasi periodic oscillations were detected not only in the optical light curve, but also in optical polarization and also in the gamma ray flux. And we had several radio images obtained with the VLBA at 43 gigahertz, different epochs, that help us to provide an interpretation. And so we explain these periodic oscillations as due to kink instabilities that developed inside the jet when an off-axis sorry, when a moving perturbation here named K traveling down along the jet off axis met a standing shock K2 here. And so one Torino team contribution to Blazar studies is the development of a geometric model to explain the long-term variability of these objects. And the idea that the orientation of the jet plays a major role in understanding the object variability was already present in our model proposed for the periodicity OJ287, and was also applied to other objects which we observed during other web campaigns, but the model was fine-tuned in paper published in 2017. And our model is a jet which is inhomogeneous. Inhomogeneous means that radiation at different frequencies are produced in the jet in different regions. In particular, radio radiation comes from a more external region with respect to the optical one. Then our jet is curved, which means the different regions have different viewing angles, and so they undergo different Doppler beaming. And finally, the jet is twisting, which means that this viewing angle varies in time, and this can happen either because of something happening inside the jet, that is instabilities, plasma instabilities, and or because of, let's say, external regions, as due to orbital motion in a binary system of supermassive black holes or precession. But this means that the Doppler beaming changes in time. And in that paper, we applied our model to the long-term optical and radio variability of the flat spectral radio quasar CTA 102, and we analyzed 9 years of data in the optical millimeter and centimeter wavelength. In this period included also an extraordinary outburst where um, the brightness of the object increased by 6 magnitudes. I cannot enter into the details of the model. Just simply, I can tell you that from the light curves at different frequencies, we derived the behavior of the Doppler factor and viewing angle as a function of times. And then by interpolating, extrapolating through the frequencies, we derive the behavior of these two parameters as a function of frequencies, which in our inhomogeneous jet means along the jet as a function of the distance from the black hole. And then having this, we could predict the shape of the spectral energy distribution of the source at different epochs and compare the prediction with the data. And we obtain a really good agreement. We can wonder whether this twisting jet model is reasonable, and of course the answer is yes. On the theoretical side, we have many results coming from magneto hydrodynamics numerical simulation, which show that inside the jet, instabilities can develop, which bend and twist the jet. And on the observational side, we again have several works where we can see that from radio observations that the ridge lines, which are imaginary lines that connect the points of maximum flux along the jet, they are bent. And also they change in time, as you can see here. So this is the last study that we submitted some time ago. Again, during 3 years of monitoring campaigns from 2019 to 2022. You can see here the optical and radial curve. And again, we reconstructed the motion of the jet emitting regions as a function of time in these two in the regions producing the optical and radio radiation, and we cross-correlated this. And just again, very briefly, from this cross-correlation, by analyzing this cross-correlation, we could infer that this twisting jet is actually made by filaments. Here is a sketch of a model. And again, there's nothing new because we know that the radio jet of extragalactic objects like M87 and 3C279 are actually observed to be made of filaments. So now our involvement in Rubin LSST, this goes back to 2017 when we became members of the TVS and then of the AGN science collaborations. We organized a couple of national meetings and the present international meeting. We wrote the Blazar section of the TVS roadmap, and we work on the metric analysis framework to analyze the impact of the survey cadence on the Blazar studies. And as Neil kindly mentioned, in the first day, we submitted a white paper in 2018 and a cadence note in 2021, which later became a paper published in a special issue of the EPJ supplement dedicated to the service strategy optimization. And just to show you a result that we obtained, we used through WEBT light curves to investigate the sampling that we will get with Rubin LSST, both in the Wi-Fi deep and the drilling field. And although we cannot get such details that we get with the web campaign, so we will be able to follow the main features of the object variability, and also to follow the spectral variability as long as the two filters that are coupled in the same night are well separated in wavelength. But in those papers, we also mentioned that Rubin LSST can be a formidable tool also to study the Blazar environment and the Blazar sensors. Blazar environment is a very nice topic to study also because it is linked to the problem to identify the parent population of Blazars. In the literature, the results on these are quite controversial. And then as for the Blazar sensors, we don't really know how many Blazars are in the sky. We made a simple calculation, and we expect about 50,000 Blazars in the widest field and about 150 objects in the deep drilling field. Most of them will be detecting single exposures, which means that we will be able to follow their variability. But the question is, how can we discover Blazars with Rubin LSST? And I invite you to follow the talk by Samantha Casadei, our PhD student, which unfortunately hurt her foot, so cannot be here, but we'll give her talk remotely later. Thank you very much.
Okay, questions?
Claudia, I think OJ287 recently missed one of the expected flares. Is there any way your model can still work in the binary scenario and still like miss one of the flares?
We haven't worked on OJ287 since 1998. I know very well that Finnish team models dealing with impact of the secondary and the disk of the primary. They, to be able to predict the flare, they have to make the model more and more complex. But still, there is always something that is missing. And so it's this. I mean, it's really a precise periodicity, and it's very complex scenario. And I should work again this to answer properly your question.
More questions? I want to ask you, I remember the discussion we had about the problem of saturation with the Stargell LSST. Where do we stand about that?
I don't really know because I cannot hear a lot inside, in the Rubin LSST environment about saturation because it's our we are going on repeating that it will be a problem because these are objects that, as I show you, can become brighter and brighter by about 6 magnitudes, and so we will saturate. And somebody told me, okay, don't worry, we will have a method to reconstruct the PSF. But I don't see really a lot of work on it. So this is an open problem to discuss, maybe.
So there are people that are working on the problem of the saturation, but in principle, it's just not for the pipeline, but after the pipeline to recover the magnitude using the wings of the PSF. The problem is that you miss all the alert of the brightest object. It's something that it's not taken into account for the moment. And the uncertainties that you will have with this method is not so accurate for making some of the science that we would like to do. So this is a real problem that there are people that are working on it, but not so many people.
Yes, in fact, in our papers, cadence note, and we suggested that it is better for us to go for 2 exposure of 15 seconds instead of just one exposure of 30 seconds. And I know, I don't know what will happen. Well, if they decide to go on with 2 exposure of 15 seconds, it will not be for our Blazar studies, I guess, but for other reasons. But we will take benefit from.
Okay, I think we have to move on. Thanks, Claudia, again. And now we have Alberto Moretti, who will talk about high blazars, right? Blazars in the early universe.
Così funziona. Does it work? Yes. So the topic of my talk will be high redshift blazar, and I have a first disclaimer. Most of the work has been done by these 2 persons here, Alessandro Caccianiga, my colleague at the Torino Observatory, and Luca Ighina, who is terminated his PhD just a few weeks ago. Since the high redshift blazar are slightly different from the object that presented in the previous talk, I am going to give you a couple of examples of the object of the source that will be the object of my talk, actually. The first object is here, is a radio loud quasar. Oh, sorry. Is a radio loud quasar, a redshift 5.3. The optical spectrum is a typical quasar, type 1 quasar. You see here the broad Lyman alpha. You see here the drop between the R band and the I band. You see here in the SED plot that is very strong in the radio band and in the X-ray band. In particular, here in the X-ray band, the emission that we detect is larger, significantly larger of the expectation from the corona. The second object, so we have basically in this object we have the emission of the jet in the radio band and X-ray band, while the optical spectrum, the optical emission, is not affected by the presence of the jet. The second object, again, is a type 1 quasar, redshift a little bit higher, is a redshift 6.4. You see here the drop between Z and I, and the emission is still significant emission both in radio and X-ray, but with respect to the previous one is much fainter. So in the context of the unified model, we can, the first object is a blazar in the sense that is observed with the jet axis very close to our line of sight, while the second object is slightly misaligned. The 2 jet emission in X-ray and radio are different because of the beaming effect. You see here the beaming as plotted as a function of the viewing angle, and you see that the first one the emission of the first one can be boosted by a factor which is higher than 1000, and even can reach a factor of 10,000. The first one here, we will call this object here as a blazar, or more specifically, flat spectrum radio quasar, because both in radio and X-ray the spectrum is hard. The second object here, we will call it slightly misaligned, with the spectrum relatively softer, both in radio and X-ray. So from this plot, you see that at the larger angle, the emission from the jet is deboosted. Actually, this means that not all the jetted quasar are actually radio loud. I would say that most of them are radio quiet in some sense. So we can use this object, the blazar and a slightly misaligned object, as a proxies for the entire jetted quasar population. It's not difficult to see that to calculate that when we observe a blazar, we can infer the presence, the existence of a 2 gamma square similar object with the jet pointing in other direction. But the key question is how many objects we can detect in a flux limited sample. The answer to this question is given by this paper, Ghisellini 2016, where they calculated the number of jetted of the observed jetted in a flux limited sample with a limit of S lim here. So basically this number is given by the sum of this ratio, which is this the flux of the blazar detected over the limit flux of the cell. So using why I think these objects are very interesting in the context in general and specifically in the context of the LSST survey. First of all, I will anticipate that we are more interested in the key element for us of the LSST survey is not the capability of tracing the light of this object, because we do not expect this strong variability in the optical band, but we are more interested in the fact that LSST will cover the southern hemisphere with a very deep limit, which is unprecedented actually. So going to why we are interested specifically in the high redshift quasar. The first reason is plotted here. The reason is that the idea is that high redshift, a large fraction of the quasar, most massive quasar actually are probably are jetted quasar. This is the density evolution of the most massive quasar. The blue line here is the general population, and the orange line here is the radio loud population as measured by this paper here. They use basically the equation I presented in the previous slide. So basically, starting from the blazar density function, they multiply it by this the factor, the beaming factor here, the Lorentz factor here. So as you can see, the radio loud density is really different from the general population density, and specifically the high redshift starting from 2 or 3 redshift, the evolution, the fraction of jetted quasar is increasing, strongly increasing. At the end, a redshift between 4 and 5, basically they found that basically all the massive objects should be jetted quasar. This result is confirmed also independently with another sample by this paper here, where they find that the density evolution of the most luminous blazar actually has a peak at 4, like in this case, which is very different from the peak of the general population. So it means that in some sense the jet probably has the jet itself has a significant impact in the evolution of these systems. The second reason is that probably most of the jetted quasar are obscured at high redshift. This is a result. This results from the use of this formula here, comparing the number of detected blazars and the number of slightly misaligned objects present in a sample presented by the paper here, the same of the formula. Actually, what they found is that the number of misaligned objects is an order of magnitude less than what is expected by this formula. So the solution they gave to this conundrum is that basically the accretion of the jet quasar is obscured, but it's not obscured by the normal torus, or usual torus, but by a bubble, an entire sphere covering all the system, which leaves only the jet coming up. This is the second reason why the high redshift, in particular, this kind of system at high redshift are very interesting. Well, very recently, in the last 2 weeks, actually, there are two works supporting this scenario. The first is this paper that will be published in a few weeks from now on Nature is a report. This reports the detection of a blazar, redshift 7, and the authors, according to the authors, the very presence of this object, this only object, requires that basically the fraction of jetted quasar, this redshift, should be larger than 50%, and most of them are obscured. In a, I would say, similar way, in this paper here, posted a few days ago on AstroPH, the authors find that the fraction of blazar, fast platinum radio quasar, in a sample of radio-selected object is significantly increasing with the redshift. So the idea is that is that most of the slightly misaligned objects are not detected, and the solution for this is again probability obscuration. The fact that so we have a scenario where most of the large fraction of the most massive black hole in the high redshift universe is as jet, and they are accreting and they are obscured. The idea that the large fraction of massive quasars as a jet can be helpful in explaining the presence of this very massive object at very high redshift. Indeed, if you assume that the limited growth, we require to assume that the black hole seeds at the beginning should be very massive. Indeed, for this object here, we would need we would need seeds with a mass that exceed 10 to the 4 solar mass. This, of course, is a theoretical problem. The idea is that if the system is characterized by a jet, the efficiency of the system changes and the growth is much quicker. And this could explain, for example, this object starting even from POP3 star remnant seeds. So we have some results on this, and we started from 2 samples actually. The first one is in the northern part, in the northern sky, the combination of these radio and optical and infrared surveys. This is the reference. So, this is another sample. The redshift of the first sample is between of the object is between 4 and 5.5. This is a little bit higher redshifted in the southern hemisphere, combining the radio service with the mass stars again and the dark energy survey. So what we find? We find results that are a little bit different from the one I presented you before. For example, here is the density evolution we found from our sample compared to the one I showed you before. So basically, using the same argument, starting from the blazar density evolution, we find that the evolution of the jetted populations is not very different, it's not significantly different from the one of the general population, which is shown here in red. Second result is that if we play with this formula here with a golden sample, a sample for which we have a good characterization of the good classification between of the beaming angle, we don't find actually any inconsistency. We have 20 blazars and 3 misaligned, which means that we have a lot of blazars. But since the flux limit is very high, actually, this is exactly what we would expect from this formula. So we do not need any. We do not to introduce any the famous obscuring bubble here. The reference of this work is here, is plotted here, and we also went a little bit further, trying to see how large is the angle that we can exclude uh, in the geometry of the dark bubble. Basically, in our sample, we cannot say too much. We can say that we see we see object within an angle which is more or less 10 degrees from the axis of the jet, which is not much, but we can with a deeper surveys, with deeper sample, we will be able to discriminate which is a measure more precisely the angle which is free from absorption. So this brings me to the last slide, which present the deeper sample we need for further studies, which is given by the combination of the LSST 8 years, 10 years survey with the new ASCAP AIMO survey here. So this is the number of blazar we expect to detect in the final LSST catalog in comparison with the object we have now, which is the two lines, black lines here. So you see that we will have an improvement of more than larger than an order of magnitude. And so I think I can summarize and make my conclusion. So I would say that the study of the high redshift jetted population of quasar are really relevant for the general population of quasars and for the study of the earlier creation of the supermassive black hole. I show you some evidence that at high redshift, a large fraction of the most massive quasars is probably jetted, and they are rapidly accreting in an obscure phase. I also show you that this evidence, I don't think this evidence is 100% conclusive, and this issue will be, well, LSST will be fundamental in studying better this issue. And so I'm done.
One question there.
Some very silly speculations. If you have all those many jets going on at very high redshifts, any implications for reionization? Any implications for star formation? Any implications for the near infrared background?
For what concerns the ionization, I would say no. There are a lot of jets, but still, well, according to the literature, the contribution of quasar should be not the dominant part, actually. So I would say no. For the near infrared background, I cannot answer. So sorry.
So for the number of, for the estimate for the number of objects, you used a gamma of 10.
Yeah.
Which is K-ish, but we have seen jets do anything from 2 to 3 all the way to 60.
Yeah.
So is there any side of how things change if you get much larger or smaller or more realistic distribution of gammas?
Well, for example, what concerns here the density evolution, I would say that does not make a big difference going from 10 to 5, for example, or 10 to 20, in terms of the shape. Of course, there is it's not really normalization, but we can probably is a real simplistic way of handling a distribution of gamma. We use only a fixed value here, but you see that we have indication that the ratio between the radio loud population and the general population here should be around 10%, and can use this to normalize all the distribution for the redshift.
Other questions? I have one. Maybe it's naive, but the presence of so many jetted AGN at high redshift, is this consistent with the accretion law that I think happened in the local universe? Is the lower mass and highly accreting?
We are talking about very massive system here, so I don't think it's very easy to compare redshift unit with the local one. But still, the idea is that the fraction at high redshift should be the local universe and the mid shift unit.
Okay. Then we move on.
Just a short comment on your question. Some people, I think Martin, Elvis, whatever, they estimated the efficiency of operation at high redshifts, and it seemed to imply higher spin of the black hole, and that eventually may be coupled with more efficient formation of that. I know not much about it.
Thanks. Thanks. Let's thank Alberto again. We have to move on. And now the last one is online, right?
Samantha? Samantha? Samantha?
Can you hear us? Yes, we don't hear her.
Yeah.
Not from here. Oh. Try say something.
Can you hear?
Yes, very loud. Wait.
Okay, share your screen.
Yeah. I don't know why not.
It's not sharing.
Some
people can share.
Problem.
What problem do you find?
It says input your screen.
Yeah.
It's their problem. You have to give the permission. For instance, on the Mac, you have to give permission.
Because the mid-ground was okay.
No, if you didn't allow the first time, it will not allow you
No, but
to share.
we
You tried?
ai partecipanti. Andiamo su talk, facciamo come abbiamo fatto con la... non ce l'abbiamo. Guarda che c'è la scerata.
Okay.
Okay, working.
Can you see my screen?
Yes. Okay.
Okay.
Just 1 second.
Ok,
Okay,
perfetto.
great. I'll tell you when you have 3 minutes left. Okay,
Okay, thank you very much.
you can start.
So today I want to present my work, which is focused on finding new laser candidates through VLASS radio data and multi-wavelength approach. There are many already known laser catalogs in literature, and here I just put these known catalogs in their sky distribution. I would say that the most important catalog is the PPCAT because it contains, it is a collection of 3,561 spectroscopically confirmed blazar. So they're not just candidates as in the other catalogs. And these blazars are also divided in flat spectrum radio quasar and VLASS. And the other catalogs are characterized by the presence of candidates selected in different ways. For example, pros and crates are based on certain objects with a flat spectral index in the radio band, while the and are based on a more multi-wavelength approach. But aside from the methods that are used to select them, there is another important difference arising, which is the number of candidates present in each of them. So we can see that they go from thousands of objects to many tens of thousands. So one of the main questions that we can ask is how many blazars do we expect? And this question has been answered in the paper of 2022, where there is an estimation, which is a lower limit of how many blazars we can expect in the sky covered by LSST, which are more than 53,000 of objects. But we're still not sure how to select them to find and select them among other objects. So the main goal of my work is to understand what characteristics are useful for their selection. And to do this, we decided to start from the radio band, and we decided to exploit the VLA Sky survey, which operates in the 2.4 gigahertz frequency, and it has a very good sensitivity per epoch and a very good resolution of 2.4 seconds. And it covers this part of the sky from minus 40 degrees and all the sky north of minus 40 degrees. Moreover, the radio band helps having a first selection of sources. And this is the total number of books that we can find in the VLASS catalog, which is more than 3 million sources. From this catalog, we started with a selection of compact sources with exploiting two parameters. One is the major axis parameter, which is the extension of the radio source expressed in arc seconds, and it is present in the VLASS table. And the other is the compactness, which is defined as the total flux, and it was already used by Ito in his paper in the selection of the pros sources. And here we have the plot of these two parameters and the distribution of the VLASS sources in the plot. And we can see that we have many sources that with a C parameter lower than 1, so with a peak flux which is higher than the total flux. So these sources take like a quality flag equal to 0, which means that we keep just the sources with no issue in the flux calculation. They are eliminated from the catalog. So we chose to keep just sources with good quality flag. And to select the compact sources, we also compared parameters with the other objects in the other catalog. And we can see that all of the objects in the other catalogs are very well defined. They are found in a specific region of the plot, with the exception of prose, which is a little bit more dispersion. So we decided to just make a cut here and keep just the objects in this box where candidates are found. In particular, we decided to cut at C equal to 2 and major axis equal to 7 in order not to exclude more than 5% of the BTCat objects. And so this is the number of compact radio sources that we have. The next step was to search for the optical counterparts. In fact, even though the main characteristic of Blazar is the flat spectral index in the radio band, we have a contemporaneity problem. So we do not have another survey as wide and as sensitive as VLASS and also contemporary to it. So the selection of sources through a radio flat spectral index could be too much uncertain. So we can mitigate this problem by taking advantage of optical data of fun stars and taking the radio optical spectral index. So in this way, the sky region covered is a little bit smaller because fun stars cover the sky north of -30 degrees. And we also decided to exclude the galactic plane for the crowding. And this is the number of sources that have a optical counterpart. So compact radio sources with optical counterparts that are 225, 477 total sources. And I also made a magnitude cut in the G-band of 23 because it's the sensitivity limit of fun stars. And then we proceeded as before. We calculated the radio optical spectral index of the BTCat, which we exploited to use as reference. And here I put the distribution of the spectral index of the BTCat blazars, dividing them in the two classes, the flat spectrum radio quasars and the VLAC. And we can see that there is a bimodal distribution with VLAC having a little bit flatter spectral index. And then we compared this distribution with the radio optical spectral index of our VLASS sample. And here, I mean, the number of objects are very different because the BTCat are less than our VLASS samples. So I just normalized the plots to better visualize it. And we can see two main things. One is that there is not a bimodal distribution in our VLASS sample. And the other one is that there is an overlapping region here of the spectral index, but also a region with VLASS objects with higher spectral indexes, mean that they have an optical flux dominant over the radio flux. And these sources could be star-forming galaxies, and they could be star-forming galaxies, but also some compact radio galaxies for classified as FR0s. So to exclude these contaminants, we decided to proceed as before and not to exclude more than 5% of the BTCat objects. So we can see that 5% of the BTCat is at the spectral index -0.3. So everything that is above the spectral index is a contaminant. So we decided to exclude it. And everything that has a spectral index lower than this could be kept. And the sources are always a very high number, which is more than 100,000 of objects.
3 minutes.
In order to make a further selection of sources, we consider the optical variability. However, variability must be taken carefully because BLAC are typically variable, but sometimes they could be host dominating. And the flat spectrum radio quasars have a, low duty cycle. They could be also possible dominant. They could also have a possible dominant discomponent and a small misalignment with respect to our line of sight. So we could have a we could also not detect outbursts or have lower variability. And to better understand the variability and the constant light curve, we started from a training set of light curves. And so we took some light curves of stars. And this is an example of a light curve of a star. And we can see that we have two main problems here. One are the outliers, which even if we have very bright objects, the outliers are always present. And the other is that the errors are underestimated. So here is very clear because in this outlier, even if it is a magnitude fainter with respect to the other points, the error bar is compared or even smaller to the other points. So I decided first to make some cleaning of the light curves. And first of all, I decided to operate as Sima et al., which made this data cleaning using this parameter that is found in the Ponstar light curve table, and also to exclude faint measurements. So I used this PSF flux over the PSF flux error higher than 5. And to try to exclude outliers, I removed the isolated points that were outside the interquartile range, but just the isolated points. And this is the clean light curves where we can see that we no longer have the outliers. However, we must always consider that the error bars could be underestimated. So making a variability analysis considering the error bars could be subject to false results. So I decided to use a method which was less dependent on the error bars. And for this reason, I used the median absolute deviation. And first of all, I calculated the median absolute deviation of my training set, okay, for stars. And this is the distribution. We can see that the median absolute deviation is quite smaller with some few exceptions. And I wanted to understand what is, I called here the noise level, because I expect stars to be constant. So there must be like a limit for the deviation that like a noise level that we can take as reference for constant and variable sources. And we can see also that the median absolute deviation is a little bit dependent with the median magnitude. I calculated the median magnitude for each light curve, and we can see that the median absolute deviation is larger for fainter magnitude. So from, let's say, magnitude 18, it increases a little bit. There is a greater dispersion. So I expect the median absolute deviation to be higher for fainter objects. So I fitted this part of the plot from magnitude 18 with a linear regression. And I found that for a magnitude limit of 23, the median absolute deviation could be is about 0.1. So I put this, I set this as my noise level. So everything that is less, has a median absolute deviation less than 0.1 could be considered as constant. And everything that has a median absolute deviation higher than 0.1 to be considered as variable source. And if I take this as reference, in my in my sample, this number of sources left. But as I said before, the this must be taken carefully because if we consider, for example, the BZCAT objects, just 50% of them are variable. So we expect to lose many objects with this kind of cut here. And here I just wanted to show you the color diagram done with Unwise. And Unwise has W1 and W2 color. So here I made an hybrid color with contrast color, but we can see that we don't have any particular region here distinguished in this diagram. With aperture Qs are found at W1 minus W2 above 0.8, as we expect for the in the quasar region usually found in literature, but the VLAC are very spread in this diagram. And here I just wanted to show you some numbers of common sources that are found in the catalogs that I listed before, but there are many sources that are not found in any of these catalogs. And also here I calculated how many sources we have in the deep drilling fields. Could be useful with the LSST data to monitor this kind of objects and their variability. Thank you.
Okay, question. Okay, one here.
Hey, Samantha. Nice talk. Yeah, because you're using the VLASS data, especially the catalog values, which is based on the first epoch. You know, the VLASS has a multiple epoch. 3 epochs has been executed so far. The years separate by the 2 and 3 years roughly. So your selection based on the compactness and the size of the sources won't change very much. If it's generally they are the intrinsically highly variable blazar, the spectral index measurement itself could be changing depending on the epochs you're using. And I
cannot hear you anymore.
Okay, let me make it short. Yeah, so the VLASS has 3 epochs, separated by 2.5 or 3 years. So 3 epochs has been executed, and your result based on the catalog probably based on the first epoch. And the parameters that you are using in the compactness and the size won't change much because even if they're varying, but the spectral indices measurement, optical radio spectral indexes might changing if they are highly variable blazars. So question is because you already know the sources, you could actually retrieve the images and compare the 3 epochs and whether they are varying, and could be useful to revise your spectral indices measurement. Also, independently, would be very useful if you look at the radio variable itself. Even though it's a 3 epochs, if they are varying between 3 epochs, it gives you sort of independent information of whether they are actually really highly variable radio sources or not. This is something you might consider if everything has been done. If you can just go to the database, you can easily pull out the images and measure the flux.
I'm not sure I understood the question. You were saying like if the variability between epochs in the VLASS it could be useful in the selection.
Yeah, not necessary for your selection based on 2 parameters, because compactness and the size won't change much between epoch by epoch. But you can independently look at if the radio flux is actually varying.
Basically, you will have here you will have independent measurement of the flux with using also the other epochs, and so you can use that to your advantage or check, the limitation of your selection based on that.
Yeah, sure, yeah.
Are there more questions? don't see more. I'm interested in something in the deep drilling field, but it is for follow-up discussion when we talk separately later. So
Okay.
I think we have a discussion now. Should we go on with the discussion or in based on the organization? Yes. Okay. So we can discuss at this point. Thanks, Samantha. I don't know if you want to stay on or you're leaving.
I'm here.
Okay. Um, we so we is there somebody who wants to comment on the Blazar part that we discussed so far?
This is just a comment for all the people interested in Blazars. In the LST broker, we have the Blazar class, and we have thousands of candidates. Nobody's using it. Just to let you know, it's a very decent classification.
In fact, I was wondering when we were discussing the other day about 5 sigma alerts, but Blazars will be the one to jump out. Immediately. But I didn't understand the point that you were making before about not triggering alerts. So are you assuming that the Blazar will be always saturated? Some will be, but
16 in it's if the saturation limit is 16 in our band, it's easy for a Blazar to reach this limit. And this is not only for the flying activity. For more or less 10% of the Blazar in the normal activity, you will not have data with this saturation problem. So, but in general, so this is a question also for the other people. This saturation problem can impact your AGN science. Yeah, because if you have object brighter than
But unless you need follow-up, you may be able to reconstruct the flag later. If you need to do real-time observation and trigger.
Just it needed to be flagged properly so that at least you know that you have an issue. Because if you take the data as they come and you try to do SD fitting for Z, for example, and you are screwed. So you needed to know that that object, that pixel were saturated. And if the data are flagged like Paola was showing 2 days ago on the depth, we do nothing. We can really compute the data. So it's going to be a problem for us as well.
But the broker, when they have the laser flag, are they treated differently in the sense that you maybe, on the other hand, you don't derive the same parameter because you know the photometry is affected, or it's just flag for now?
I think it's from the point of view classification, the fact that Blazars are affected by this, it's contributing to the classification. We measure exactly the same attributes for all the first because we don't know firsthand the class. And then maybe I haven't checked that, but maybe this is helping the classifier because we can find with a very high Blazar candidate. So yeah, maybe this is affecting the features, but it's also contributing to the classifier.
Yeah, so somebody just raise your hand so I can get you the mic.
Yeah.
I didn't.
Thank you. Just to address your point about saturation. So yeah, Mara. So I'm just checking the schema, and any every single pixel that is saturated in the so you will have that information. That's for the DRP. I'm less certain about what the alerts will say, whether it's got saturated pixels. But if you're doing your kind of stuff with the DRP or for the DRP, then that information is fine.
Okay.
For all the people working on high redshift sources or those that are working using colors and not only variability on one band, I was wondering how many of you are correcting the photometry for galactic extinction and IGM while doing the calculations and the number expectation and so on, because I think that I never heard these words being mentioned in the entire 3 days we were discussing. And as long as you are working with one band only, it's fine because you are going to be safe. But as soon as you start to work colors, and I heard the importance of colors during this presentation, you need to correct for galactic extinction because this is to affect your colors depending on where you are on the sky. And if you're looking for high redshift sources, you need to take into account after redshift 2 of the IGN absorption. So for the broker, I was wondering whether you also have this information. We cannot expect that machine learning will learn also about that because before learning, you need to have a million of sources. There's so many things that need to be learned. So I was wondering how many of you are already having these two ingredients in the simulation, expectation, or whatever prediction.
So at the moment in the LERSA, we don't have that correction, and actually we rely on this extension from the Milky Way to have it if the source is galactic or not. That is looking currently the CTF model at least. But yeah, that can produce problems for high redshift objects. But we at the moment we only have single band variability features with the periodogram, which is not affected by this. But we are planning to have this for LSST, so we plan to include an extension map part of the process. So yeah, it's coming. Yeah, for all the sources. Not AGN, like you mean intrinsic from the host? Yeah.
Absorption that produced the Lemon forest. We needed to correct for that as well because our slope is going to be affected by it again if you use colors.
Yeah, the thing is depends on what are your plans with. So if you are only doing classification, maybe this will help you to identify where you see high redshift objects because you will see these effects in the color. But if you want to do science like physics with the data, then
So how you record? You're the one tennis match. How you recognize the object? How you identify them if you don't correct the data for the IGN?
yeah, well, at the moment with the bands we have, I think with CTF it's hard to do the experiment, but yeah, we should test this with more bands testing.
Mara, I'm afraid I don't understand. So with the IGM, this is a problem above redshift 3, 4, 5, but a random object in the sky, we don't know what the redshift is. And so we've Sure, but that's already going to be baked into the training set that you use to train the classifier. Okay, so you're
Just a question to somebody because I'm not really an observer. Is the extinction towards deep drilling fields also high? I mean, because they were probably selected in such way that the Milky Way extinction does not affect them much.
It's generally lower, but and the point is the area is smaller, so at least internally the variation are smaller, so it's less. Yeah, but usually the low extinction field. I don't know all of them. Like the Chandra fields, low, it's a very low extinction. Yeah, exactly.
That the extinction was higher than desired, but because of the coordinate choice at the time of the observation, that was the ideal field. It is not because it is equatorial, so it it is having more extinction than desired.
Just on the theme of extinction, if these blazars are, as I suspect, in dust-rich lenticular galaxies rather than elliptical galaxies, which tend not to have much dust, you have colours that are reddened because of dust. In the local universe, your dust-rich lenticular galaxies, you can have 1.5 mag extinction in the B band and less in the R band, and depending on the redshift of your source. Yeah, it's going to be changing luminosity of blazar AGN by an unknown amount because you don't know the information of the disk. And when I say disk, I mean the galaxy disk, the lenticular galaxy disk. If you get inclination, then you might have some chance of correcting dust, but there's dust evolution with a function of redshift. So I think it's a bit messy trying to get a handle on the true intrinsic luminosities because of the dust in the host galaxy. Just a comment.
Just to follow up what Matthew was saying, so at least from our experience with CTF, we have the data release and the classifiers that are able to separate redshift, and that means above 3, and the results are very good. The thing is, this color effect helps you to identify them. We are finding them mostly because of the color, not because of the variability, because it's the variability of the redshifts. So I think for redshift up to 4.5, we will be okay. Then for very high redshift objects, probably with variability, you won't be able to identify anything because it's like time scales are too long. But from our experience, only with CTF, that only has what we are using GNR, it's okay. But then for LSST, you will also have the I band and the Y band. And from our experience with Ultravista, you can easily find hybrid objects with the I band. So with LSST, this problem will be solved because we will have more bands. And the training set will be affected by this as well. So, but if you really want to find the outliers, like high redshift objects, other techniques can help.
Okay. There are urgent comments. Otherwise, in the meanwhile, we get a couple of announcements.
Yes, for those participating in the social dinner, you can see here, we will have the dinner at the Trattoria, which is kind of restaurant, Loca Fola. This is the address, and we can be there at 8 p.m. And this is the map. You can reach it, for instance, by metro from Porta Nova or. Okay. So if you agree, we will now take a group picture upstairs, and then we will have the coffee break. After the coffee break, we will show the plenary, the Monday plenary session that was given at the Rubin Community Workshop. And if you are interested, otherwise you can just relax, and the buses will take you back to Torino. Okay? At what time? What? You have to consider 1 hour for the plenary, so it will. Now we are late, so it's about 5:30. About. Okay. Sì. Un po' presto, 4:30. Allora non finiremo alle 5:30, ma alle 6:30. Yeah. It's probably, yeah, 15 to 6. Okay.
We will leave from with the bus. Then 1 hour. Take a 20-minute break.
Okay. So. Yeah. It was something that we discussed, and there were people interested, and also because it may be interesting for tomorrow's general discussion. That it would if you prefer to have a look in, I don't know, later, or we can discuss whether there are people interested in this, or if you prefer to go back to Torino just after the coffee break. There are yeah, one possibility is to ask one bus to go, but if it isn't enough to bring. Yeah, 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 yeah. 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 So, tomorrow is full. I mean, the meeting is ending after lunch, and then somebody's leaving even before. May I ask you how many people are interested in seeing the plenary session? One, two, three. Yeah.
Yeah, exactly.
How many people would like to go to Torino just after the coffee break? I didn't see it. I don't know how it is organized.
My suggestion is let's go for the coffee break. We'll
First the photo.
yeah, sorry, first the picture, then during the coffee break maybe we can take a look at the plenary just fast and see if we can maybe the important part is half an hour. I think everybody can resist half an hour. Not many people want to stay a full hour here. No, del fatto che
alla fine quando vuoi togliere della fine, sì, Madonna, grande grande tecnico.
Okay, let me give you an update on what the program is. We checked through the video, and the interesting part about the jump, the presentation, the welcome, and so on, is about 30 minutes. Describe the current status of the telescope operation and so on. So we think we can resist 30 minutes, and then the final part, I think, is questions, so that you're welcome to watch them on your own at home. And so we'll shorten by half the time. Okay.
This is not related at all to this. So we are organizing taxis for tomorrow to leave directly from the planetarium to the airport at more or less at 2 p.m. If you are interested, let me know because we are only Diana and I. Okay, another one. Good. But two, right? Only one? Oh, okay. Okay. Let me know. That's it. Thanks.
Okay. So if we are fine, we can start the projection, and so we have also time to then rest at home.
The current status and the readiness for operations. This is the big message for the week. Rubin Observatory is nearing completion. That is just an outstanding image that was taken a little while ago by Olivier Bonin from here at SLAC. We have made tremendous progress this year, not only by our construction team, who is outstanding and continues to work really hard on our behalf. Our stakeholders, our lab and agency stakeholders have worked tirelessly to help us get there. And of course, you all. You have committed time and resource and all your good input to get us as far as we've gotten so far. So that is the big message for this week. I think we should celebrate where we're at. We're not there yet, so let's be a little bit careful. But we've done a lot, and it's been over 20 years that people have been working on this project, and we're now on the precipice of being able to start the science that we all want to do. So let's take a little bit of tour. It's been an amazing year since January. We started up there in the upper left-hand corner by finishing the dynamic testing in Chile of the telescope system with the commissioning camera and the mirror assemblies with their surrogate mirrors on them. So that was important dynamic testing that had to be done before we could assure ourselves that we could put the glass on the telescope, which is what we're up to now. M2 was tested individually, and that's a picture of some of our in-kind contributors, our colleagues from Italy who did great work on M2. We've added other site monitoring equipment recently. In this case here, you're seeing a picture of another in-kind contribution with the Dream camera, which is an all-sky camera that we use during operations. And then in March, it really started to pick up and get super exciting. So that's a picture there of the M1, M3 coming out of its warehouse where it was stored elsewhere on the summit and making its way up to the facility. And after that happened, which happened very successfully, that's an amazing picture, by the way. It sure looks like it's hanging over the edge there. But it all worked out. And after that, it's just been every few weeks, something really great has been happening. So let's just go through it real quick. Going clockwise, what you see is that big mirror that had been on the summit, ready to go for years, had gone up there right before the pandemic. It was taken out of its crate, and then this great team from the University of Arizona, the Richard Karras Mirror Lab, came down and recoated it with a protective coating, which is what you see in blue, and that helps the vacuum attachments with the lifting fixture. And it was put on its cell, which is the Rubin teal colored structure there on the upper right. And that's right after it was lifted onto the cell, and then the lifting fixture is already coming up off it at that point. And this is a picture of our coding team and mirror team, or part of the mirror team, with the mirror on the cell underneath the coding chamber before it had been, that blue coating had been stripped off and prepared. But they did that. They put it under the chamber. That's with the chamber just above it, and it will come down. And then, of course, not long ago, they put on very nice coating of silver on that M1, M3, and it looks fantastic. The throughput will certainly be very good from that point of view, from that one element. We continued by taking the commissioning camera off, which had been mounted on the telescope used for those dynamic tests. We also removed the M2 with its assembly and surrogate mirror. And then we took M2 out of its box. It had also been on the summit for quite a while. It had been coated some years ago. And then the team, just a few weeks ago, actually put it right on the cell there in the lower right-hand corner and attached it. And it is now waiting and ready to go back up to the main telescope soon. Actually, it should be installed on the telescope this week or next. And then, of course, a lot of great stuff has happened with the camera, as Risa was just telling us. So I think it was in April, the team had finished testing and started packing everything up, and they had a nice celebration with the entire team here. That's what you see here on the upper left. They packed the camera up, it went into its shiny travel bag, and then into that container. I understand the President of the United States actually stopped by to see it. There was some cover story that he was on a fundraising event or something, but he was in the area. I'm sure it was to see the camera. Anyways, it along with about 10 other truckloads of gear and supplies and materials all got loaded very smoothly onto this 747. Two of our intrepid engineers flew with it all the way to Chile just to make sure. And then it arrived and they met other members of our team. And then they got it to the mountain. So this is, I just love this picture on the upper left. It's just this regular truck stop on the way between Santiago to La Serena or Cerro Pachon. And you see there's our trucks and there's all these, the team was traveling in all these other 4x4s, and they just pulled over and had a nice lunch, and then they kept going on their way. No major issues. You can talk to Aaron if you want to know some of the details, but everything basically went smooth. The trucks made it to our property outside of La Serena on the way up to the mountain and stayed there overnight. I think the truck drivers camped in their trucks. And then the next morning, here on the lower right, they made it up to the summit facility and were welcomed with a lot of excitement by the team. The camera was opened up. All of it looked good so far and was put into the clean room where it is right now. And this is just a wonderful picture of all the folks from SLAC, from the construction team in Chile, from a few folks from Noir Lab, just the people from all over the project that were there that day, many of them playing key roles to get us to this point. And I just love that picture of this moment where we got the camera up to the mountaintop. The camera is in the clean room. They're making great progress with its reintegration. We hope to get a rough pump on it in the next couple weeks, and that will tell us that the vacuum's ready to go. They are working on the filter exchanges. There is a pinhole in there right now, and they'll get to glass in August. The cryo lines, all important cryo system, is being assembled and pumped down in the lower facility, not on the telescope yet. And then soon we'll start up the pump coolant system and check out the readout electronic boards, and we'll be on our way. We hope that the focal plane cooling can start maybe by the end of this month, maybe a little bit later. Stay tuned. So what is next? Next is commissioning. We're going to go on Sky. This is just an amazing moment. There's all the key assemblies. M1, M3 coated. That's a beautiful silver coating. M2 is ready to go. M1, M3, we're still working a little bit on the connections inside the cell to the system. We'll get that done soon. M2 is just about ready. ComCam is cold right now and starting to take data. So we're just about ready to put everything up on the telescope and get on sky with the commissioning camera, while LSST cam goes through its reintegration testing there in the facility. So these are the big milestones to look forward to. We'll put the M2 on the telescope, I said, next week or this week. ComCam will go on after that. And hopefully by about the end of August, M1, M3 will be fully on the telescope, and right away in early September, we'll turn on ComCam. And then we'll wait till about the end of the year to start putting LSST cam on the telescope. So this is what 2024 looked like. We put the LSST camera in Chile, check. Primary, tertiary mirror, coated it on the cell, check, check. Secondary mirror on the cell, check. ComCam next, LSST cam, November, December, and then cooled down, tested out, ready to go, hopefully early next year. System first light will happen about the March timeframe with an associated celebration to follow. You'll hear all about it. And then the legacy survey space and time can start later in FY or by the end of 2025. The operations team has also been busy. We have a lot going on. We've been planning, implementing things, testing, and we're getting ready to go. So lots of procedures, lots of plans have been documented. We have built up the US data facility and the rest of the data processing capability, and that's ready to go. We've been working on the baseline cadence with the survey cadence optimization committee. There has been testing of the full systems end to end, which I'll say a few words more about in just a second. And there's been ops rehearsals that are right now tuned very carefully to make sure we're efficient with commissioning data, but a lot of what they're learning will flow right into operations. So the team everywhere is doing more and more things that look like operations as we get closer to that point. We will make sure our staff are fully trained. Obviously, they're getting a lot of work right now on everything from data processing, the long-haul network, the data facility, to how to run things at night, to all the things to maintain and operate the system in Chile with many of the same people working on the construction project going into operations. We will have a review later next year after the surveys that show our science validation are done. And then we'll declare the system ready after meeting a few key criteria, which, by the way, we talked a little bit about today at the SAC meeting, if you happen to come to the SAC meeting later today. And then we'll go for starting the survey. I love this picture. This is a picture of a team. Actually, most of them are contractors, I think, a contracting group that we work with a lot in Chile called RIL. And they're doing lots of things on the dome and other things. But one of the things they're doing right now in the last few weeks is working on cleaning out the dome. So this is a real phase change from a construction project to a working observatory. That dome has to be a new, clean, managed environment when we put glass and the camera on the telescope. And so these folks literally are going around with handbags, with wipes and everything. They're cleaning out the entire inside of the facility. They're picking up little bits of material that have been dropped, little scraps, and they're making it ready to really start moving those big sub-assemblies up to the top of the observatory. And that's been happening the last couple of weeks. So it really is a change that's happening evident right now. We have been commissioning, and we continue to commission. We've been using our auxiliary telescope, the small 1.3 meter telescope up there that will be used for atmospheric characterization eventually. But it's also a test bed for our software and other processes as we go forward. So this is our main control room from which we operate that telescope, and we've been working with it over the last year or so, and we continue to do so. We run the scheduler. We run pipeline processing every night that we take data with this telescope. The data go from the taking of the data automatically on the summit over the long-haul network. They're processed here at the US data facility at SLAC, and then provided for the commissioning team and operations team to work on. So this is an example of a little mosaic taken with the scheduler on the lower right and difference imaging, which we're doing now as well. On the upper left there. We have had 2 successful operations rehearsals. This shows the team that was on the first one, I think, and they were there running a set of simulated images that were literally like they were captured off a commissioning camera, sent to the data facility, processed. Meanwhile, the team at the summit was doing all the things they would be doing with real data at the time, including verification, validation, what worked, what didn't work. It's a real example of observing. This one tuned to commissioning for sure, but eventually we'll get to the real operations. It's been quite successful. We learned a lot. Every bit of it was useful. And we keep pulling that in. This was, I think, a couple months ago, and then we just finished another one a couple weeks ago. So we're making real progress as we go forward. One of the key things, obviously, to start the survey is that we have the right cadence, so we know what we're observing as we start, and we're efficient as we go forward. So last year, the Survey Cadence Optimization Committee, which is led by our Deputy Project Scientist, Federico Bianco, and community members. This is not an internal project thing. This is really the community members sitting on this committee and taking input from you all to make sure your science is included in how we analyze simulations of the survey so that we can assess how well it's going to do for each type of science. They have been working very hard. They delivered a phase 2 recommendation last year that made big strides forward. We improved the overall wide pass deep aspect of the survey, added the Virgo cluster. We improved how the internight visits would work. We finalized the assignment of at least 5% of time on the deep drilling fields and 3% of time for the target of opportunity follow-up, but without a detailed plan for what that would look like. And then we settled on this idea of a rolling cadence, which is an idea where you concentrate on different bands of the sky more intensely rather than uniformly observe everything straight through. And that allows you to get shorter time scales for transient and variable star work. So that recommendation led to further work this year on finishing up the details. I would say we're well over 90% done with this, and we will finish it by the end of this fiscal year. The team, led again by Fed and the SCOC, continues to work. They just put out a baseline 3.4 reference for the survey. We're working on specific details. We're working on understanding, I think, the idea is that we may move, the SCOC is going to recommend that we move to 1 30-second exposure instead of 2 15-second snaps. We'll see how that works out. We want to get commissioning data first before we fully make that decision. So that'll be coming soon. They are working out right now the details of what the cadence in the deep fields will be. There's a few Milky Way details to be left or to be decided on. For example, the filter balance. They have folded in a huge improvement of the overall survey from the aluminum coating on M1, M3, and recommendation for the TOO program that came out of this Rubin TOO 2024 workshop, which was held over the day in Berkeley earlier this year. You can see that there's a link there. If you get the slides, you can see that report in full. So those are the kind of details that are being settled out, and we'll have that final recommendation by the end of this year. There will no doubt be a few things that we'll carry forward that we won't decide on right now. And of course, we will evolve the survey as needed by monitoring our progress throughout the survey and using the SCOC and our scheduling team to make the decisions to continue to improve on what the survey can deliver. We will talk more today in detail at a session at 2 p.m. here in Kavli on Rubin Early Science Program. This is the science that we're trying to enable from now through data release 1. So data release 1, again, will capture the first 6 months of LSST data in operations, and then we'll start processing it while we continue to take data, but it won't be a full year of data yet. And it will also include the science of data that comes out at the end of the commissioning period, the so-called science validation surveys. How we do that is through a series of data previews. Many of you have been involved in data preview 0, which is simulated data. Simulated data from our colleagues at DESK, and also a solar system catalog. DP1 will be a data preview from commissioning camera data, so that will come out in the next months. The data will come in the next months. We won't release those data to the community until after first light, so that's early next year. And then data preview 2 will again be the first real science data for the community that will come out after the science validation surveys are complete at the end of commissioning. So we'll be working on producing that data preview while we start the survey going forward. We need effective template generation. So you recall that we need templates around the sky to generate alerts. So we will do an incremental generation of templates throughout the end of commissioning through the first part of the survey. That will allow us to do some alerts in the first year on those places where we have good templates, but we'll have to be effective and make choices about where to observe and which filters to observe. So that's a key component of early science. That world public stream of alerts will start sometime toward the end of commissioning and will steadily grow as we go forward until it's up to full strength after data release 1 and we have the full set of templates around the sky. And then data release 1 will come out and then we'll be off and running into the future. So this is just kind of a graphical description of what I just said. Sometime early next year, we'll hit this system first light, which is a technical milestone for the project. And then we'll be on to system optimization and running toward the start of the survey. In that time, we will have the first look event for our media, celebrating our success that we have a system that takes science-ready images. We'll put out data preview 1, which will again be the ComCam data that we've taken in a few months. And then we're talking about a first look at LSST cam data that comes out sometime after first light that would be perhaps part of the first light images, maybe something else as we go forward into the rest of commissioning, but we're discussing that right now. What will happen as we run toward the start of operations is we'll start producing nightly visit images and catalogs, and those will become available with more and more confidence and less latency as we go forward. At some point when we're convinced that we have the right processing and everything is working well, those will become a regular nightly production. Remember that any particular image is embargoed for a short amount of time, but after the first period, we will then be putting out images every night. And then the community alert broker integration will happen here, and then we'll build toward full alerts as we go forward toward DR1. Just a real quick note, if you haven't gotten involved in DP0 and want to get ready, I encourage you very much to go to the Rubin Science platform online, lsst.data.cloud or data.lsst.cloud, and get on there and start working with our community science team to spin yourself up on how to use the tools and what the data will look like. This is tremendous. This team has brought in over 1,300 people with new accounts over the last couple of years as we've gone forward. We're looking toward something like 10,000 users eventually, so this is a good down payment on that. But really, if you haven't got involved yet, come talk to us. We're happy to talk to you no matter what your level of familiarity or experience is with large data sets. That team is led by Melissa Graham, who might raise her hand. Talk to Melissa if you have any questions about DP0. This is a high-level chart for the operations team about when these data releases come out. So it just sets down with a date range, the things that I've just been talking about. The idea is that those dates on the right, the end dates, will stay more or less fixed, and the certainty of the early date will compress. And you can see that's happening if you've seen earlier versions of this plot that we've shown as we get toward the data previews, the first light and start of operations, and then we're adding in the current view of where we're at. So there's January 1st, 2025. We'll get first exposure to real data with commissioning camera April, May next year. Routine alert generation will follow toward the beginning of the survey, and the first science data set, DP2, early in 2026, probably. Just a few words about the in-kind program. I know many of our international collaborators are here, and we're glad that you are, and we're happy to collaborate and have you with us. We have 28 countries right now that are participating as full members of the collaboration, working together, and they're making contributions to our science enterprise as we go forward. We have 2 major contributions from the UK and France in our data processing and delivery of our data releases, and that actually that work is going quite well. And of course, one of our most important partners is Chile as our host country, and some of our Chilean colleagues are here with us this week as well. A few things about data rights agreements. We have actually signed one, which is good news, and we look like we're sending out more. We have about 7 of them that have been delivered now to teams, and we'll be working with them both on the Aura and Slack side to get those out and get those done before we start operations, of course, in a year. We wanted to let you know that the 2-year grace period for junior associates who move or get promoted into permanent positions has been clarified or modified slightly. So you can go look at the data rights policy to see what that's all about, or ask Phil or I if you have questions. And the data rights holder list is public, and you can go find that as well. Our in-kind program coordination team, which is led by Aparajita Verma, who is either in this room or one of the other rooms, will be having a session this week too, and you can check in with them if you have any questions. There's a number of in-kind sessions this week. We are modestly expanding the in-kind program as needs develop. So when the community comes with needs, identified needs, we will take those on board, and that will give an opportunity to programs to propose to meet those needs. So it starts with the community, that is you all, or maybe the observatory, identifying a need, posting that, and then people in the in-kind teams and programs can propose to meet that need and thereby grow their program. I wanted to say real quickly, thank you to our committees. You do a tremendous amount of work for us and on behalf of all of us. So thank you very much. The Science Advisory Committee is active and will be meeting today. The Users Committee is meeting later. Users Committee is meeting later this week. They are also quite active and a great place for you to give your input. Our Contribution Evaluation Committee is active, but doing less right now because the main in-kind program is well on its way. I mentioned the Survey Cadence Optimization Committee, again, a really important committee based on community input. We will have a Data Policy Committee, not yet convened, and we're working hard to get our Resource Allocation Committee up. That's the ones that will help us allocate computing resources as we go forward that are above and beyond your normal allocation. We will have, we have an important committee that we work internally with the Chilean community called the Implementation Committee that just makes sure we do the things that we said we would do in our agreement so that we can operate in Chile. And then we're working with Rubin and Roman as well, and you'll hear more about that later this week. And of course, we work constantly with the science collaborations. This is the Users Committee. Those that are circled in orange are here on site, and we thank you for your service. And if you folks have any questions for the Users Committee, those are the folks that you can contact this week. Look out for the Science Collaboration Plenary on Wednesday. You'll hear all about it. And for right now, Gautam Narayan is taking over for Will Clark, who's on leave, as the coordinator for the Science Collaborations. Real quick now, because I'm running out of time, we will have achieved first light by the time we get to the next RCW. That's just a tremendous milestone and something we can all be proud of and excited for. So this is well underway. We're making lots of plans with our stakeholders and the agencies. You'll hear all about it as it happens. The EPO team is working constantly on engaging the community and the public and building momentum as we approach first light. So you'll see a number of these science releases. It's really, we want the excitement of Rubin not just to be that we got there and we had first light and there's this great system. It's really about the science. What is the science we're going to do? And we want to continue to tell that to the public, so that by the time they see first light, they're going to be really excited about seeing what the science is that we're going to do in the next 10 years. So that's my status for you all. Just excited to be here with you. has been a great first half of the year, and it's going to be another great year going forward, not without challenges. We're going to have a great data set for this broad and diverse community. And by the time we meet next, we'll have had first light, and we'll be on the precipice of starting this thing that we've been working so hard on, and we'll be ready to capture the cosmos. I want to say one more thing. I said the big message was that we're close to getting on sky, and we really are. We're going to be observing soon. The other big message is we're going to do it together. We have gotten this far along over 2 decades because we've worked together. It's not just the Rubin Observatory. If it was just the Rubin Observatory, we'd be done. Nothing the Rubin Observatory does will have the impact and the value that it can have without the community. So it's really together. You, the community, have done so much to bring us to this point with the developing of the science and your effort to help us get the system that we all want together. So it's going to be a challenging year, but if we do it together, we stick together, we're going to get there real soon. Thank you.
All right, we have time for a few questions. And for a first one, while people in this room think, and while Jeff and Greg out there in Redwood and Trinity, while you look for hands in your rooms too, we'll start by going.
So I guess we will not ask questions. So what you're welcome to discuss, I guess, this point on the bus, right? So for me, unless the organizer have changed, for today we're done, and I hope I see you to the social dinner. Thank you.